Ever looked up at the night sky and wondered where all those glittering stars come from? It's a story of cosmic dust, immense potentials, and the most powerful force in the universe, gravity. And it all begins in the quiet, dark corners of our galaxy. Across the cosmos, vast, cold clouds of gas and dust drift silently through space. We call them molecular clouds. They're like giant, cosmic nurseries, just waiting for something to happen. These clouds are enormous, stretching for hundreds of light, and they're made mostly of hydrogen and helium, sprinkled with tiny grains of dust, the leftovers from ancient, long-dead stars. For millions of years, these clouds can just float there, in a delicate balance. The tiny bits of gas and dust are always moving, creating a gentle outward pressure. But lurking in the background is gravity, the silent architect of the universe. Gravity is constantly trying to pull everything together. In these clouds, it's a cosmic tug-of-war between the outward push of gas and the inward pull of gravity. So, what tips the scales? What gives gravity the upper hand? Sometimes, it's a shock wave from a nearby supernova massive star exploding in a spectacular cosmic fireworks show. Other times, it could be the gravitational ripple from two galaxies colliding, or simply a random, dense pocket of gas that forms by chance. Whatever the trigger, it compresses a part of the cloud, cramming the dust and gas closer together. This is where gravity's magic truly begins. As the material gets denser, gravity's pull gets stronger, and a stronger pull means it can gather even more gas and dust. It's a feedback loop, a snowball effect, on a cosmic scale. The denser it gets, the stronger gravity becomes, and the more material it pulls in. A small clump begins to grow, pulling matter from its surroundings, becoming the center of attention in this vast, dark cloud. This collapsing core of gas and dust is called a protostar, a baby star. As it pulls in more and more material, the pressure at its center starts to skyrocket. Imagine squeezing a bicycle pump. The pump gets hot, right? The same thing happens here, but on an unimaginable scale. The immense pressure from all that collapsing gas causes the protostar's core to heat up, reaching millions of degrees. It starts to glow, not from nuclear fusion just yet, but simply from the intense heat of compression. It's like a cosmic ember, shining brightly within its dusty cocoon. Around this glowing protostar, the leftover material doesn't just fall straight in, because everything in the cloud has some slight rotation. As the material gets pulled inward, it spins faster and faster, just like an ice skater pulling in their arms. This spinning material flattens out into a disk, known as a protoplanetary disk. This swirling disk of dust and gas is not just leftover material. It's the birthplace of future planets, asteroids, and comets. Our own solar system, including Earth, was born from a disk just like this. The protostar continues to grow, feeding on the disk around it. For hundreds of thousands of years, it's a messy, chaotic process. The young star is often hidden from view, shrouded by the thick dust and gas it's still accumulating. But astronomers can peer through this cosmic veil using infrared telescopes, which can detect the heat radiating from the hidden protostar. As the core of the protostar gets hotter and denser, it finally reaches a critical point. The temperature and pressure become so extreme, we're talking about 15 million degrees Celsius, that something incredible happens. Hydrogen atoms, the most basic building blocks of the universe, are forced together so violently that they fuse to create helium. This process is called nuclear fusion, and with that first spark of fusion, a star is born. The moment fusion begins, an enormous amount of energy is unleashed. This energy pushes outward from the core, creating a powerful force that finally counteracts gravity's relentless inward pull. The star stabilizes, entering a state of equilibrium, a perfect balance between the crush of gravity and the explosive power of fusion. This is the main sequence, the long and stable adulthood of a star, where it will spend most of its life. Our own sun is currently in this phase, and it has been for about 4.6 billion years. What happens to the rest of the cloud? The newborn star doesn't just sit there quietly. It unleashes powerful stellar winds and intense radiation that blast away the surrounding gas and dust, clearing out its cosmic nursery. This process reveals the brand new star, shining brightly for the universe to see. often alongside its newly formed planetary system. It's like a grand unveiling. So, the next time you gaze at the stars, remember what you're seeing. Each point of light is a testament to gravity, its incredible power, its ability to take something as humble as cosmic dust and, over millions of years, forge it into a magnificent, light-giving star. From a quiet cloud to a blazing sun, it's the greatest construction project in the universe, happening right now, all across the sky, or where they're going. Today, we're embarking on an epic cosmic journey to uncover the incredible life stories of stars. From their explosive births to their spectacular deaths, it's a tale of gravity, fire, and cosmic recycling. It's more dramatic than any blockbuster movie. So, buckle up as we explore the life cycles of stars. It all begins in the vast, cold emptiness of space, inside what are called giant molecular clouds. These aren't your fluffy, white, Earth-sky clouds. Think of them as colossal, sprawling nurseries of gas and dust, mostly hydrogen. They're so huge, they can stretch for hundreds of light years across space. For a long time, nothing much happens. But then, something disturbs this peaceful giant maybe. A shockwave from a nearby supernova, or the gravitational pull of a passing star. This disturbance is the trigger. It causes pockets of gas and dust within the cloud to start clumping together. As more and more material gets pulled in by gravity, these clumps become denser and hotter. This dense, hot core is called a protostar. It's not quite a star yet, but it's the baby version, glowing faintly from the heat of its own compression. Imagine squeezing a ball of clay. The center gets packed tightest. That's what's happening here, on a mind-boggling scale. Now, here's where the magic happens. As the protostar continues to gather mass, the pressure and temperature at its core skyrocket, reaching millions of degrees Celsius. At this critical point, a process called nuclear fusion ignites. Hydrogen atoms start smashing together to form helium, releasing an immense amount of energy in the process. This outward push of energy perfectly balances the inward pull of gravity. The protostar has now officially been born as a stable, shining star, entering the longest and most stable phase of its life, the main sequence. Our own sun is a main sequence star right now, and it's been happily burning for about 4.6 billion years. But not all stars are created equal. Their mass is the single most important factor that determines their entire life path. Think of it as a fork in the cosmic road. We have two main categories: small to average stars, like our sun, and massive stars, which can be dozens of times bigger. Let's first follow the path of a smaller star. For billions of years, a sun-like star will steadily fuse hydrogen into helium in its core. But eventually, that hydrogen fuel starts to run out. Without the outward pressure from fusion, gravity begins to win the battle again, and the core starts to collapse. This collapse, however, heats up the outer layers of the star, causing them to expand dramatically. The star swells up, becoming hundreds of times its original size, and its surface cools, turning a reddish color. It has become a red giant. If this happened to our sun, it would expand so much it would swallow Mercury, Venus, and possibly even Earth. Inside the red giant's core, the pressure and heat become so intense that a new fusion process begins. Helium starts fusing into heavier elements like carbon and oxygen. This gives the star a temporary new lease on life. But for a star the size of our sun, that's where the fusion process stops. It's just not massive enough to create the conditions needed to fuse carbon. Eventually, the helium fuel in the core is also exhausted. The star becomes unstable. It begins to puff away its outer layers into space in gentle waves. This expanding cloud of gas and dust, illuminated by the hot, dying core, creates one of the most beautiful objects in the cosmos. A planetary nebula. Don't let the name fool you. It has nothing to do with planets. They were just named that because they looked like fuzzy, round planets through early telescopes. And what's left behind at the center of this beautiful nebula? A tiny, incredibly dense, Earth-sized core called a white dwarf. A white dwarf is the cooling remnant of the star's heart. It no longer produces energy through fusion. It just sits there, radiating away its leftover heat for trillions of years, slowly fading into a cold, dark object called a black dwarf. It's a peaceful, quiet end to a long life. Now, let's rewind and take the other path of the massive stars. These are the rock stars of the universe. They're born big, stay alive fast, and they die young and go out with a bang. A massive star, being so much bigger, has way more gravity. This intense gravity creates incredible pressure and heat in its core, causing it to burn through its hydrogen fuel at a furious rate. While a star like our sun lives for about 10 billion years, a massive star might only live for a few million. When a massive star runs out of hydrogen, it also expands, but on a much grander scale, becoming a red supergiant. Betelgeuse in the constellation Orion is a famous example. Inside its core, the fusion process doesn't stop at carbon. The immense gravity is strong enough to keep crushing the core, igniting successive stages of fusion. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. But iron is a dead end. Fusing iron doesn't release energy. It actually consumes it. So, when the core of the supergiant becomes a solid ball of iron, the energy production suddenly stops. In less than a second, the delicate balance between gravity and pressure is shattered. Gravity wins. Catastrophically, the iron core collapses in on itself at an incredible speed. This collapse triggers a titanic rebound shockwave that blasts the star's outer layers into space in one of the most violent and powerful events in the universe. A supernova explosion. For a few weeks, a single supernova can outshine an entire galaxy of billions of stars. It's so bright you can sometimes see it in the daytime sky. This explosion is also crucial for life as we know it. It scatters all those heavy elements, the star-created carbon in our bodies, the oxygen we breathe, the iron in our blood across the cosmos. We are literally made of stardust, forged in the hearts of dying stars and scattered by supernova. After the supernova, what happens to the collapsed core depends on its mass. If the remnant is between about 1.4 and 3 times the mass of our sun, the crushing force of gravity is so intense that it smashes protons and electrons together to form neutrons. This creates an object of unimaginable density, a neutron star. A neutron star packs more mass than our sun into a sphere just a few miles across. A single teaspoon of neutron star material would weigh billions of tons. But if the core is even more massive, more than about 3 times the mass of the sun, then not even the force between neutrons can stop the gravitational collapse. Gravity becomes completely unstoppable. It crushes the core down to an infinitely small and dense point called a singularity. This creates a region of space-time where gravity is so strong that nothing, not even light, can escape. A black hole is born. It's the ultimate end, a final, mysterious stage in the life of the most massive stars. So, there you have it. From swirling clouds of gas and dust to stable main-sequence stars, swelling red giants, beautiful planetary nebulae, and faint white dwarfs. Or, for the cosmic heavyweights, a short, brilliant life leading to a universe-shaking supernova, leaving behind an exotic neutron star or an enigmatic black hole. The death of one generation of stars provides the raw material for the next, in a continuous, grand cycle of cosmic birth, death, and rebirth. Have you ever looked up at the night sky and wondered what secrets lie hidden in the deepest, darkest corners of the cosmos? Beyond the twinkling stars we see, there are objects so extreme, so much they challenge our very understanding of physics. Today, we re-dive in headfirst into the abyss to explore 2 of the universe's most fascinating and mysterious creations, black holes and neutron stars. So, what are these cosmic behemoths? Both are the grand finales of massive stars, much larger than our own sun. When these giants run out of fuel, they can no longer fight the crushing force of their own gravity. The result, a spectacular explosion called a supernova. What's left behind depends on just how massive the original star was. Let's start with neutron stars. Imagine taking a star 1.5 times the mass of our sun and squishing it down into a sphere, just 20 kilometers across, about the size of a city. The gravitational collapse is so intense that protons and electrons are forced together to form neutrons. That's why they're called neutron stars. They are one of the densest objects in the known universe. A single teaspoon of neutron star material would weigh about as much as Mount Everest. Can you even fathom that? But their density is just the beginning. Neutron stars are also cosmic lighthouses. They spin incredibly fast, some rotating hundreds of times per second. As they spin, they emit powerful beams of radiation from their magnetic poles. If one of these beams happens to sweep across Earth, we detect it as a regular pulse of energy. We call these flashing neutron stars pulsars. It's like a cosmic clock, ticking with unimaginable precision. Neutron stars are also home to the strongest magnetic fields in the universe. Some, called magnetars, have fields so powerful they are a quadrillion times stronger than Earth's. That's a 1, followed by 15 zeros. This magnetic field is so intense it could wipe a credit card from halfway to the moon and would distort the atoms in your body from thousands of kilometers away. These objects are truly extreme. But what happens when a star is even more massive? If the leftover core from a supernova is more than about 3 times the mass of our sun, not even the dense-packed neutrons can stop the gravitational collapse. Gravity wins. And it wins in the most spectacular way possible. The core collapses infinitely, crushing down into a point of zero volume and infinite density, called a singularity. This is the birth of a black hole. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape. That's why they're black. They don't emit or reflect any light. Surrounding the singularity is an invisible boundary called the event horizon. Think of it as the point of no return. Once you cross the event horizon, there's no coming back. It's a one-way trip into the unknown. For a long time, black holes were purely theoretical, a strange consequence of Einstein's theory of general relativity. But in recent decades, we've found overwhelming evidence that they're real. We can't see them directly, of course, but we can see their effects on the space and matter around them. For example, we can watch stars orbiting what appears to be empty space. By tracking their orbits, we can calculate the mass of the unseen object they're circling. If that mass is packed into a small enough space, a black hole is the only explanation. This is how we discovered the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A, which has a mass of over 4 million suns. We can also detect black holes when they're feeding, as gas, dust, and even entire stars get pulled in. They form a swirling, superheated disk around the event horizon, called an accretion disk. The friction in this disk heats the material to millions of degrees, causing it to glow brightly in X-rays and other forms of light. So, paradoxically, the regions around black holes can be some of the brightest places in the universe. And in 2019, humanity achieved something truly historic. The Event Horizon Telescope, a global network of radio telescopes, captured the first ever direct image of a black hole's shadow. It was a fuzzy, orange donut of light, but it was monumental visual proof of these cosmic monsters. So, let's put them aside. Neutron stars are incredibly dense balls of matter you could theoretically stand on, if you could survive the gravity. Black holes are even denser, but they aren't objects in the same way. They are poor warped space-time, a hole in the very fabric of the universe. A neutron star has a surface. A black hole has an event horizon. One of the biggest mysteries connecting them is what happens when they collide. Thanks to gravitational wave observatories like LIGO and Virgo, we can now listen to the universe. When two neutron stars spiral into each other and merge, they send out ripples in space-time gravitational waves. These cataclysmic events are thought to be the universe's primary factories for heavy elements like gold and platinum. The gold in your jewelry was likely forged in the collision of two neutron stars billions of years ago. When a black hole and a neutron star collide, it's even more dramatic. The black hole's immense gravity can literally tear the neutron star apart before swallowing it, a process that also unleashes a torrent of gravitational waves. And when two black holes merge, that creates the most powerful gravitational wave signals we've ever detected. A cosmic symphony announcing the creation of an even larger black hole. These events are opening up a whole new way to study the universe. Gravitational wave astronomy allows us to probe the interiors of neutron stars and test the limits of general relativity in the extreme environment near a black hole's event horizon. So, what lies ahead? One of the biggest unanswered questions is what happens inside a black hole. Our current laws of physics break down at the singularity. To understand it, we need a new theory, a quantum theory of gravity, that can unite Einstein's relativity with the strange rules of the quantum world. This is one of the holy grails of modern physics. From city-sized stellar remnants to cosmic voids that swallow light itself, neutron stars and black holes represent the ultimate extremes of nature. They are the graveyards of stars, but also the crucibles where new elements are born and the laws of physics are pushed to their absolute limits. The more we learn about them, the more we realize how much we still have to discover about our incredible universe. Have you ever wondered where everything around us comes from? The chair you're sitting on, the phone in your hand, even you yourself? The answer is stardust. Literally. But that's only half the story. The universe isn't just a one-time creator, it's the ultimate recycler. Today, we're diving into the epic tale of cosmic recycling, the grand celestial process that dismantles old worlds and stars to build new ones. Let's start at the very beginning. About 13.8 billion years ago, the Big Bang created the first elements, mostly hydrogen and helium, with a tiny sprinkle of lithium. That's it. Imagine trying to build our complex world with just those three ingredients. You couldn't. So, where did the oxygen we breathe, the carbon in our DNA, and the iron in our blood come from? The answer lies in the first stars. These primordial stars were giants, hundreds of times more massive than our sun. And because they were so massive, they lived fast and died young. Inside their scorching hot cores, they acted as cosmic forges. Through a process called nuclear fusion, they slammed lighter elements together to create heavier ones. Hydrogen and helium fused into carbon, oxygen, neon, and so on, all the way up to iron. But creating these elements is one thing. Getting them out into the universe is another. This is where the death part of the cycle comes in. When these massive stars ran out of fuel, they couldn't support their own immense gravity anymore. They collapsed in on themselves and then exploded in one of the most spectacular events in the cosmos. A supernova. This explosion is unbelievably powerful. It not only flings all those newly forged elements out into space at incredible speeds, but the energy of the explosion itself creates even heavier elements, like gold, silver, and platinum. Everything heavier than iron on the periodic table was born in the heart of a supernova. So, the next time you look at a piece of gold jewelry, remember, it was forged in the explosive death of a star billions of years ago. So now, interstellar space is seeded with these heavy elements. They drift for millions of years as vast, cold clouds of gas and dust. We call these clouds molecular clouds or stellar nurseries. They're beautiful, ethereal structures. But they're also the construction sites for the next generation of stars and planets. Within these clouds, gravity begins to work its slow, patient magic. It gently pulls the dust and gas together. As a clump gets denser, its gravitational pull increases, attracting even more material. It's a snowball effect on a cosmic scale. Eventually, the core of this collapsing clump becomes so hot and dense that nuclear fusion ignites once more. A new star is born. But what about the rest of the material? Not all of the gas and dust goes into making the star. The leftover material forms a swirling, flat disk around the newborn star, called a protoplanetary disk. And this is where the magic of planet formation happens. It's cosmic recycling in its purest form. Inside this disk, tiny dust grains remnants of ancient, long-dead stars start sticking together. Think of it like dust bunnies forming under your bed on a mind-bogglingly vast scale. Grains become pebbles, pebbles become rocks. Rocks smash together to form larger bodies called planetesimals. These planetesimals, some kilometers wide, continue to collide and merge. It's a chaotic, violent process. Over millions of years, the largest of these bodies sweep up most of the material in their path, growing larger and larger until they become full-fledged planets. This is how our Earth and all the other planets in our solar system were formed. About 4.5 billion years ago, from the recycled ashes of stars that lived and died long before our sun ever existed. And the story doesn't end there. The recycling continues. Comets and asteroids, which are leftover building blocks from this era, still bombard planets. They can deliver water and organic compounds, essential ingredients for life. Area on Earth, geological processes like plate tectonics and volcanism are another form of recycling. Rock is pushed deep into the earth, melted down, and then erupted back onto the surface as new land. Even life itself is part of this grand cycle. When organisms die, their organic matter decomposes and is recycled back into the ecosystem, providing nutrients for new life to grow. The carbon atom that is in your little finger right now could have once been part of a dinosaur, and before that, part of a star that exploded billions of years ago. This cycle isn't just something that happened in the past. It's happening right now, all across the universe. As we speak, old stars are dying, enriching the cosmos with new elements, and distant nebulae, like the famous Pillars of Creation and the Eagle Nebula. New stars and planetary systems are being born from that recycled material. We are living in one moment of an eternal cosmic dance of creation and destruction. What's truly amazing is that this recycling process is essential for life as we know it, without the death of those first stars. The heavy elements needed for rocky planets and biological life would never have been distributed throughout the universe. We need carbon for our cells, iron for our blood, calcium for our bones, all materials that had to be cooked in a star and then recycled. So, when you look up at the night sky, don't just see a collection of twinkling lights. See a vast, dynamic, and interconnected system. See the ghosts of ancient stars that gave their lives to create you. See the stellar nurseries where future worlds are being assembled from their remains. The universe is not a static place. It's constantly rebuilding, reinventing, and recycling itself. The atoms that make up your body have been on an incredible journey, spanning billions of years and light years of space. From the Big Bang to the core of a star, through a supernova explosion, across a vast molecular cloud, into a protoplanetary disk, and finally, becoming part of a small blue planet, and eventually, you. You are not just living in the universe. The universe is living in you. We are all made of stardust, recycled and reformed into something new and wondrous. It's a humbling and awe-inspiring thought that connects us to the very fabric of the cosmos. On one hand, it's the life-giving heart of our solar system, the source of all warmth and light. On the other, it's just one of billions upon billions of stars in our galaxy alone. So, which is it? Is the sun an ordinary, run-of-the-mill star, or is it a cosmic miracle? Well, the truth is, it's both. And today, we're going to explore this fascinating paradox. Let's start with the case for the sun being, well, kind of average. Astronomically speaking, our sun is a G-type main sequence star, often called a yellow dwarf. Now, dwarf might sound small, but that's just a classification. It is actually more massive and brighter than about 85% of the stars in the Milky Way. Most stars are tiny, dim red dwarfs. So, in that sense, our sun is a bit of an overachiever. However, when you look at the stars you can actually see in the night sky with your naked eye. Most of them are giants and supergiants, making our sun seem pretty humble in comparison. The sun is also middle-aged, about 4.6 billion years old, with another 5 billion years or so left before it exhausts its fuel. It's not a hot-headed, fast-burning young blue giant, nor is it an ancient, fading ember. It's in its stable, predictable prime. This stability is incredibly common for stars of its type. It also doesn't have a stellar companion. Many stars exist in binary or multi-star systems, dancing around each other in a complex gravitational tango. Our sun, however, is a solitary star. While not exceptionally rare, it's another tick in the not that unusual column. So, from a purely statistical standpoint, if you were to pick a star at random from a lineup, you could very well end up with one a lot like our sun. It's a reliable, steady, single yellow dwarf, a common sight in the cosmic neighborhood. But hold on, this is where the story gets truly miraculous. While the sun's Characteristics might be common. Its specific combination of traits and its location are extraordinarily fortunate for us. Let's start with its stability. That boring, predictable, middle-aged phase is the golden ticket for life. Young, massive stars are violent and short-lived. Red dwarfs, while long-lived, are known for their violent, planet-scorching flares. Our sun, however, has a remarkably stable output. It provides a consistent stream of energy, allowing for the stable climate and liquid water that life on Earth needed to emerge and evolve over billions of years. This isn't just lucky, it's practically a prerequisite. Then there's its mass. If the sun were much more massive, it would burn through its fuel in a few million years. Not nearly enough time for complex life to develop if it were much less massive, like a red dwarf. The habitable zone, the Goldilocks region where liquid water can exist, would be much closer to the star. A planet in that zone would become tightly locked, with one side perpetually scorched and the other frozen in darkness. Our sun's mass puts the habitable zone at a perfect distance, allowing Earth to have a day-night cycle and a stable environment. Let's also talk about metal. In astronomy, metals are any elements heavier than hydrogen and helium. These heavier elements are forged in the hearts of dying stars and are essential for forming rocky planets like Earth and, well, life itself. Our sun has a relatively high metal. This means the primordial cloud of gas and dust from which our solar system formed was rich in the building blocks of planets and people. We are literally made of stardust, and our sun happened to be born in a neighborhood rich with the right kind of dust. And what about its location in the Milky Way? Our solar system resides in a quiet, suburban lane of the galaxy, in what's called the galactic habitable zone. We're far from the chaotic and radiation-blasted center, where a supermassive black hole resides. We're also not out in the sparse, metal-poor fringes of the galaxy. We're in a sweet spot, a relatively peaceful spiral arm with enough heavy elements to build worlds, but not so much cosmic traffic that we're constantly bombarded by supernova or other catastrophic events. It's like finding the perfect, quiet street in a bustling metropolis. Furthermore, the sun's journey through the galaxy is remarkably calm. It follows a nearly circular orbit around the galactic center, staying within the flat plane of the galactic disk. Other stars have more eccentric, roller coaster-like orbits that plunge them through the dense and dangerous spiral arms far more frequently. Our sun's gentle, predictable path has shielded our solar system from many potential cosmic calamities over billions of years, giving life an uninterrupted chance to flourish. So, when we put it all together, a new picture emerges. Is the sun an average G-type star? Yes. Is it a single star of a common age? Absolutely. Absolutely. But is its existence, in its specific location, with its specific mass, metallicity, and incredible stability, anything short of a miracle for life on Earth? Not at all. Our sun is the ultimate cosmic paradox. It's ordinary enough to be one of billions, yet extraordinary in its perfect suitability for us. It's a reminder that sometimes the most profound miracles aren't the flashy, ratty exceptions, but the quiet, steady, and perfectly timed coincidences that make everything possible. It's the unremarkable star that makes our lives remarkable. It's a humble celestial powerhouse, and it's ours. The next time you feel the warmth of its rays on your face, take a moment to appreciate this beautiful contradiction, our very own ordinary, miraculous star. Thanks so much for watching this cosmic journey with me.